Yeah, it's on. Okay. Welcome, everybody. And again, sorry a bit. Yeah, all the lectures are being put up on this webpage. So you can watch them there if you missed something. And I guess, yeah. Okay, so remember last time what we ended up with, well, we don't really need Unitil here, was this continuous functional calculus, and it's very important. So let me just recall it here. If we have a normal element, which just means that we have an element which commutes with its adjoint, then this map called little gamma from the span continuous functions on the spectrum of A. So remember, this is vanishing at infinity in the event that it's not unital, but in the unital case, you don't need that. The C-star algebra generated by A and the unit, if there is one. So as a subalgebra of A, what does this do? This maps the function that takes Z to Z, so just the identity, and maps that to A. This is a star isomorphism. And if we have some f continuous function on the spectrum of A, then f of A is also normal. So f of A, I should say this is going to be, of course, gamma of f. This is normal. And we have this spectral mapping property again. I guess that was actually a separate theorem, so let me just recall the numbering. The spectrum of f of A is the same as f of the spectrum of A. And if we have some continuous function G in the spectrum, continuous functions on the spectrum of f of A now, and things compose exactly how we want them. So we have that G of f of A is the same as G of f of A. Okay, so really this is an extremely useful theorem. We will see in this next section on positive elements just how useful it is. It will really be used quite a lot. Okay, so section 3, the topic for today is positive elements. These are somehow a very key feature of any C-star algebra. So have ourselves C-star algebra A. And we say that an element A is positive if it's self-adjoint. And remember that a self-adjoint element has spectrum in the real numbers. So for A to be positive, we ask that it's actually contained in the positive reals. And I will denote the set of positive elements by A with a little plus at the bottom. Okay. So let's prove some things about this set of positive elements. First, quick definition. Probably you're familiar with this, but let me write it out anyway. If we have a set S with a binary relation, then we call it a partial order if it satisfies the following. So it should be reflexive. So X is always less than or equal to itself. We want it to be transitive. So whenever we have three elements, X, Y, and Z in S, if X is less than Y and Y is less than Z, then we want that X is less than Z. And finally, we want that it's symmetric. So if X is less than Y and Y is less than X, then X is equal to Y. Good point. Thank you. Okay, so this positivity condition allows us to define a partial order on the self-adjoint elements. So how do we do that? Well, take two self-adjoints. And we say that A is less than B. If the element B minus A is positive. The fact that we can put an order structure on the self-adjoint elements is again a very key property of C-star algebras. And okay, the first two are not so difficult to check. So for reflexivity, obviously A minus A is 0, which is positive because its spectrum is 0. So that's certainly in R plus. So that's good, it's reflexive. Anti-symmetry, again, is relatively easy for essentially the same reason. If we have that the spectrum of A minus B is in R plus, and the spectrum of B minus A, which is just the minus of the spectrum of A minus B by the spectrum mapping theorem, then these are both going to be 0. Which means that the norm of A minus B and B minus A is 0, so we get that A is equal to B. For 2, note that, so what is the assumption here? If A is less than B, B is less than C, then B minus A is positive, and so is C minus B. And we want to show that C minus A is positive. So we can write C minus A as C minus B plus B minus A. So transitivity will follow from the fact that the sum of two positive elements is positive, but we will prove that a little bit later on. So that little bit is postponed for a moment, but we will come back to it. Okay. All right. Another fun application of the functional calculus is that every positive element has a unique positive square root. So by square root, what I mean, if we have element B such that B squared is equal to A, then we call B a square root of A. So first, a lemma, let's show that this is true for continuous functions. And then we can use the functional calculus to derive it for more general C-star algebras. So let X be a locally compact Hausdorff space, and let F be a positive element in C naught of X. And F has a unique positive square root. Okay, so let's show that, first of all, such a square root exists. Okay, so F is a positive element, which means that it's self-adjoint and its spectrum is contained in the positive real numbers. What is the spectrum of a continuous function? Well, it's just the values it takes. So that means that for every x and x, f of x is greater than or equal to 0. So for every x, this number here has a positive square root. Namely, of course, f of x to the half. So we can define f to the half in the obvious way. F half of x is just f of x half for every x in x. Okay, well, some elementary analysis tells you that this is indeed a continuous function, and its values are in R, and in fact they're in R plus, so indeed f half is a positive element. Okay, so we want to show that this is unique. So suppose we have some other positive square root. So g squared is equal to f, but it's not equal to f half. Okay, if this is true, then there exists some x such that these two functions take a different value. So such that g of x minus f hat of x, f half of x is non-zero. Okay, and by assumption, g and f are also both positive elements. So this implies that since this is non-zero, that g of x plus f half of x is strictly greater than 0. Then we have that g minus f half, well, let me stick in the x's. In the wrong spot there, sorry about that. So what is this? Well, we get a g squared, and that's f. And then, of course, since this is commutative, these two terms cancel out, and then we get minus f, which is 0. And that gives us a contradiction. So, in fact, we must have had that g is a half. So that completes the proof. And that allows us to following. Every positive element in a C-star algebra has a positive square root. Okay, so proof. First note that if A is 0, then the only possible square root is 0. So we can assume that A is non-zero. Okay, since A is positive, we know that the spectrum of A is in the positive real numbers. So we can take a function in the spectrum of A satisfying is greater than 0, and f of x equals, f of x squared is equal to x for every x. Okay, A is positive, it's self-adjoint, so in particular it's normal. So f of A is a well-defined element of the C-star algebra. And we can set A half equal to f of A. Then this is evidently a square root of A, since we know that under this isometric map that A gets mapped to this function here, one that's just the identity x. And now suppose that we had a different square root. We also know that this is positive by this spectral mapping theorem we just had. So it's a positive square root. Okay, suppose that B is another positive square root. Okay, well, if B squared is equal to A, then B will commute with A. And then we can approximate A half by polynomials to conclude that it must also, B must also commute with 8.5. So if we look at the C-star subalgebra generated by A half and B, it's commutative. And since it contains A, it will also contain the spectrum of A in its spectrum. So now uniqueness follows from the lemma. That is a commutative C-star algebra. Okay, so So this allows us another nice feature of unital C-star algebras, which is that they are spanned by unitaries. So just recall that a unitary is something that commutes, it's adjoint, and it's equal to the unit of the C-star algebra. Okay, so proof. So recall that we showed already that if we have an element, arbitrary element, then we can write it as the sum or as the linear span of two self-adjoints. So indeed, it's enough to show that unitaries span the set of self-adjoint elements. And furthermore, since we can always write A as and obviously this is in the linear span of this, we can assume that our elements have norm at most 1. Well, sure, yeah. I mean, 0 times any unitary is 0, so that's in the linear span of unitaries trivially. Right? For here. Sure. Well, of course, I mean, we could have, it's clear that 0 is in the span of the unitaries, so might as well assume A is non-zero. Okay, sure. Okay, so enough to show it's true for elements with norm at most 1. Okay, so let A be such an element. Okay, well, then A squared will be a positive element, since certainly it's still self-adjoint, and now we're taking squares, so they're going to be, the spectrum will now be in the positive reals. And since A is less than 1, we have that 1A minus A squared is also greater than 0. And maybe to convince yourself of this, it's useful to draw a picture. So we know that A is some, under the functional calculus, we have the spectrum of A is contained in the real line and bounded on either side by the norm of A, and A is this element here. So that's A. So A squared looks something like this, but by assumption, 1 is somewhere up here. And this is also in this commutative C-star algebra generated by A and 1, so this picture makes sense. And then you see that indeed 1 minus, so this is A squared. 1 is here. Indeed, that's going to be a positive function. So this has a positive square root. And we can let U1 equal A minus I square root of this element. And U2 will be A plus. And you can check, it's very, just by multiplying these out, that indeed these are unitaries. And we have that A is equal to the sum of half U1 plus half U2. So we've shown that that is a sum of two unitaries, a linear combination of two unitaries which by our assumptions is enough to show that that's true for all elements in the C-star algebra. Okay, so this next result will allow us to conclude what we had before about this less than relation on the self-adjoints being a partial order. Because we will show that the positive elements form a closed convex cone in the C-star algebra. So convex cone. Subset of a vector space that's closed under linear combinations with positive coefficients. So the positive elements in A is a convex cone, and in fact, it's a closed convex cone. Okay, so let's prove this. So first of all, notice that if we have some positive element in A, then how is this defined? Well, it's self-adjoint, and its spectrum is contained in the positive elements. And how do we define a spectrum if A is non-unital? Well, we take the spectrum of the unitization. So that means that an element in A plus is positive. So if A is non-unital, then note that A is in A plus if and only if it's a positive element. This should be A and A. A and A. Then that's a positive element if and only if it's positive in the unitization. So we can assume that A is unital. Okay, so first of all, if A is in A and lambda, sorry, A plus and lambda is greater than or equal to 0, then lambda A is quite clearly also going to be positive, since it's self-adjoint, since this guy's real, and what is the spectrum of this guy? It's just going to be lambda times things in the spectrum of that guy. So to see that A plus is indeed a cone, we just need to look to see that the sum of two positive elements is positive. And remember, this is also what we needed for proving that it was a partial order. Okay, so here's first a claim. If we have a self-adjoint function in C of x for some compact subset of R, and we can find some positive, well, zero positive, not strictly positive, but just positive R such that the norm of this function f minus R is less than or equal to R, then we have to have that f is greater than 0. So proof of the claim if R is 0, then of course this forces f to be 0, which is positive. So suppose now that R is greater than 0, but that f is not positive. So what does this mean? That means it has some element. So it's by assumption real valued. It must have some, there must be some point x for which f of x is negative. Okay, but in this case, at this point, we have f of x minus R. This will now be strictly larger than R, which means that the norm of f minus R, which is sup of f of x minus R for all x and x, well, that's then greater than R, which contradicts our assumption and proves the claim. So all right, so this suggests we would like to turn this into a argument using the functional calculus, which is indeed what we shall do. Well, this is strictly negative. So sorry, the question there was, can this be equal to R? But it can't, because this is actually an actual negative number. It'd be equal if it was 0, but we're excluding that by assuming contradiction that it's not positive. Okay, so now let's take two positive elements. Well, it's clear that at least the sum of two self-adjoints is again self-adjoint. So it's normal. So we can identify the C-star algebra generated by A plus B and 1 with continuous functions on the spectrum, which is now a nice commutative C-star algebra. And under this identification, remember that A plus B gets mapped to the function that's identity. So we want to show that A plus B is positive. Again, this identification is an isometry, so it's enough to show that F here is going to be positive. So we'll use what we just saw in the claim by taking some R. And what will R be? Well, it's going to be the norm of A plus the norm of B, which is a perfectly nice positive real number. Okay, so since A itself is greater than 0, then we know that, again, by the claim, A minus the norm of A is less than A. Okay, actually, this is not immediate from the claim. Maybe I should have pointed out that this R trick works for any R that's at most the norm of the function here. And then similarly, we have that B minus the norm of B. So this is, again, really to be a little bit more precise, that's the norm of A times 1, because we're able to assume that we're in the unital setting. And now we get to use the almighty triangle inequality. So just using the triangle inequality and putting in these observations, we get that this is indeed less than A plus B, which means that A plus B indeed is positive. So it remains to show that A plus is closed. So let B be the set of positive elements whose norm is at most 1. What is this? Well, we can rewrite this as all those elements A, such that A minus 1A is at most 1, and A is self-adjoint. Now, it's fairly obvious, I guess, that that the set of self-adjoint elements is closed. So any limit of self-adjoint will again be self-adjoint. And since we have this less than or equal condition here, it's clear that so is this set. So B, the set B here is the intersection of two closed sets, so itself is closed. And hence, RB is closed. But what was B, A and A plus with norm at most 1? Well, RB in that case is the same as R times A plus, which is just A plus. So indeed, A plus is closed. All right. So first, just a little observation, again, using functional calculus, that we can always write a self-adjoint element as the combination of two positive elements. So, and in fact, in a very nice way. So if A and B are in positive elements, we say that A and B are orthogonal if they multiply to 0. And of course, if A, B is 0 and these are positive, then we can take the star here. We still get 0, and then that's BA is equal to 0. Okay, so let's take some element that's now self-adjoint. And Again, what does the self-adjoint element look like under the functional calculus? Well, it's just this element here. Oops. Assuming I can actually make it go through the origin. So here's A. We can always write A as the sum of two positive elements, or sorry, the span of two positive elements by taking this minus this. So I will call this guy A minus and this guy A plus. And to be more precise, let F plus F minus in continuous functions on the span of A be the functions defined as you see in the picture. So F plus X, this is going to be X when X is greater than 0 and will be 0 if X is less than 0. And F minus will be X if X is less than 0 and 0 otherwise. Then you can see from this picture here that A is going to be the sum of A minus and A plus, and moreover, A minus and A plus are orthogonal. So we've shown the following. The unique decomposition into positive elements. Which are orthogonal. So maybe I should say into orthogonal positive elements. A plus and A minus. So I guess we didn't really prove uniqueness here, but I'll leave that as a exercise. So as a corollary, we get that the set of self-adjoint elements with this partial order is actually upwards directed. So for every A, B, and A, there exists some self-adjoint element C such that A is less than C and B is less than C. Okay, so it's clear that this is true for positive elements. We just take A plus B. And well, positive elements span self-adjoints, so that gives us the corollary there. And now we come to another interesting theorem, which, am I going to end with this? Not quite. Okay. Which somehow tells us that this whole notion of positivity in the C-star algebra is actually very much related to the star structure. Perhaps a slightly surprising way. What number are we on? 3.1.10. For every element A star A is positive. Okay, clearly this is going to be self-adjoint, but we would like to show it's positive. So first, so we're going to use the fact that we can write a self-adjoint as a combination of two positive elements. And let's first see that this can't be negative in the sense that minus A star A cannot be an A plus unless A is going to be 0. So suppose that minus A star A is a positive element. Then recall from perhaps the first lecture that we know that we can swap these two elements and get that the spectrum of minus A star A is the same as minus A star. And again, this is clearly self-adjoint. And if this guy is positive, then so is this guy. Okay, so now let's write A as the sum of self-adjoints. And we can calculate this, so it's going to be B squared. Since B is self-adjoint, we don't need the star there. And then we get IBC plus wait a second, that's a lie. This is a minus, plus IBC plus minus C squared, since again C is self-adjoint. Okay, so what does this tell us? Well, these guys obviously cancel, and we already saw that wait, why do I have a minus? Do I want to have a minus? I should have a plus. Yes, sorry. Okay, Fine. So what does this tell us? That so it's the sum of positive. Now I've done something funny here. I think this is maybe CB. Is that right? Okay. Well, in any case, we can show that this is also positive, but then that means that this has to be 0. Yeah, sorry. Shouldn't have tried to skip some steps, but okay, this should be actually, because we're going to swap things, this should be no, this should be CB. Well, okay. Okay. Right. So in this case, A has to be 0. So we can assume now that A is non-zero. Then we know that minus A star A cannot be positive. So we know that A star A itself is self-adjoint. We can write it as B minus C, where B and C are positive and orthogonal. Now we would like to show that C is 0, and that will give us the result. So consider the element AC. What is this? We get minus C star A star A C, but of course C was assumed positive, and in particular self-adjoint. So we get this here. Now we sub in B minus C for A star A. B and C are orthogonal, so we get that this is C cubed. And since C is positive, so is C cubed. And you can draw yourself a nice functional calculus type picture. Right, so we have that minus AC star AC is greater than or equal to 0, which gives us that a C is equal to 0. And remember what C was. So if A is this guy, oops, really gotta improve my aim here. That's A, C was this. So the only way for A times C to be 0 is if C itself is 0. So indeed, A star A sorry, this should be A star AC. Okay. So that's the proof of that. And let me just try to sneak in here. That notice that that means that in fact A plus is exactly this set, because we showed that every positive element has a square root, so you can always write A as which is of that form if A is in A plus. Wait, I might not get through everything I wanted to, but okay, let's just keep going. Anyway. Okay. So more about this order on the self-adjoints that we get from having these positive elements. So we want two self-adjoints, and let's take A less than B. And we have the following. For every element C, we can take C star A C and compare that to C star B C, and this will preserve this order. If A is less than B, then its norm has got to be less than the norm of B. And if A happens to be unital, and we can talk about inverses, and these behave how you would expect, namely that B inverse will be smaller than A. Okay, so A is less than B, which means that B minus A and A plus has a positive square root. Then C star BC minus C star AC is equal to the square root of B minus A times C all starred B minus A C. And we just saw that this is positive. So indeed, by definition of this relation, we have that C star AC is less than C star B, C. Okay. So without loss of generality, let's assume that A is unital. And of course, we can do this because remember that if A is non-unital, then it's there's an isometric copy of A inside its unitization, so we don't change the norms. Okay, then by functional calculus, we get that B is less than the norm of B times 1. So again, here's B. Here's B times 1. Clearly, this is less than that. So we get that A is bounded by, since as we saw, this relation is transitive. Now, this is just a scalar multiple times 1A, and we know that this map is isometric. So that means that this relation holds here in the commutative C-star algebra. Which is just, of course, B. So now we just need to show 3. Can I fit it in the bottom of this chalkboard? And let's see. Not really. All right, so we want to show that B inverse is less than A inverse. So first, note that if C happens to be invertible, then if lambda is in the spectrum of C, we must have that lambda inverse is in the spectrum of C inverse. So in particular, A inverse and B inverse are again self-adjoint. Did I say, yeah, I guess I didn't say there was a. Okay, now using one, we have seems I'm about to claim they're positive. Okay, so we can also assume that A and B are positive. By scaling everything if necessary. Okay, and then in this case, the spectrum will again be contained in the positives. So these will be both positive. So in particular, B minus half is a positive element, which is well defined. And we have that B to the minus half A, B minus half is less than which is obviously just the unit. And now we can apply 2. We see that this guy has norm at most 1. And what is this? This is missing a half, aren't I? A half so in particular, this means that this element A half, B half also has norm at most 1. And then again, we can apply the C star equality, since we can now flip these, because taking the star of something doesn't change anything. And we get that, oops, there's a minus missing. Sorry about that. This is a minus. Again, by the C star equality, we get that A half B inverse A half has norm at most 1. So in that case, we get again by 1 that let's multiply on either side by a minus half. So and now we know that this is less than 1. Which is of course A inverse as we wanted. Okay, so it's now 1 p.m., which means I should stop. Yeah, okay, I will just stop there, and next week I will be at a conference, so Tristan will take over for me. So see you guys in 2 weeks.